Today we start looking at the behavior of rational functions. So we spent some time looking at how you operate them, but what's the behavior? So we'll do a quick review. Definition of a function. For every input, there's exactly one output. You can use the vertical line test to see if something is a function. So we looked at several function shapes in first semester, and this semester, starting with, we looked at quadratics this semester, and we know a quadratic is a U-shaped graph or a parabola. Okay, and then we talked about how that function shifted. So if we just sketch the original function, the mother function, we know that the vertex is at 0, 0. All right, we knew how to shift the graph up, down, left, and right. So to review, the plus 7 shifts it left 7, up 5. And we knew the minus 4 is right, 4.5, and down 32. So these are questions you've been asked the whole semester and last semester. All right, let's review this. Write the equation of each line. This one right here, the y-intercept is 2, the slope is 0. So this equation is y equals 2. All along that line, y is 2. For part B, our equation would be y equals negative 3. The y-intercept is negative 3 and the slope is 0. It's flat. When you have a vertical line, these are x equals line. So all along this pink line, x equals negative 2. No matter what the y value is, x is negative 2 all along that line. And for this right here, x is 4. All along this vertical line, x would have a value of 4. Goal today, intro to rational functions. To review, a rational function is a ratio of two polynomials. Today we're going to learn what an asymptote is. So first, let's graph the function. Here's our new mother function for the rest of the unit, 1 over x. This is a rational function. It can be written as a fraction. So let's plug in and graph this. So if we plug in a negative 4, this is 1 over negative 4, which is negative 0.25. So let's put that here. If we plug in a negative 3, this is 1 over negative 3, which is negative 0.3 repeating. If we plug in a negative 2, we get negative 0.5. If we plug in a negative 1, we get negative 1. If you plug in a 0, it's undefined. Because if you try to divide by 0, the number's so big, again, we say it's undefined. 1 divided by 1 is 1. We have 0.5, we have 0.3, and we have 0.25. All right, so let's graph this. So negative 4, negative 0.25, negative 1, negative 1. Okay, let's go the other way. 1, 0.5. Okay, so we graph it, looks something like this. Let's use our graphing calculator to figure out or to get a better idea of what that would look like. So I'll just open a graph page and type in 1 over x. And here's what it looks like. So we were able to get some of the points, but we can see that there's two invisible boundary lines. So one is at x equals 0, and one is at y equals 0. So we're going to draw those in. I'll use dash lines. All right, so there was no graphs that passed that. Here was what our function looked like. So here is the mother function of a rational function, the function 1 over x. And so a new word, a line that a graph approaches but never reaches, like an invisible boundary line, is called an asymptote. The equation of the vertical asymptote is at x equals 0. It's the y-axis, but it's the line x equals 0. The equation of the horizontal asymptote is the x-axis, which is y equals 0. The domain and range of the function are all possible x and y values. So if we take a look at our graph, we say our domain, x cannot be 0. So if you look at that, all the x values have a graph associated with it, except for at 0. There's no graph there because of the asymptote. So the asymptote helps us with our domain. And same for the range. What's the only y value you don't see on this graph? And there's a y value everywhere, except for here at 0. And so we say the domain is everything, or the range is everything, but it can't be 0. So if you can figure out the asymptotes, the domain and range is going to be everything except for your asymptotes. All right, so here's a real-world example of a rational function. So we have Hermann Ebbinghaus tested memory, and he learned that there's this thing called the forgetting curve, which is your retention of knowledge is strongest right when you learn it, but then it decreases as time goes on. So it's called the forgetting curve. And that is this function 1 over x. It's an example of that function 1 over x. So we have to learn how to look at the behavior of this graph and be able to explain it in this unit. So if we take a look at the first example, can you write the equation of each transformation of the parent function 1 over x and give the vertical and horizontal asymptotes? So our equation, if it's 7 units to the left, we would say y equals, and left and right is inside the parentheses and opposite of what you think, so x plus 7. The vertical asymptote, remember they're at 0. X is 0 and y is 0. But if everything shifts left 7, so will the vertical asymptote. So that will become x equals negative 7. The horizontal asymptote remains the same. Okay, let's do another one. Let's say we shift the graph 10 units down and 4 units to the right. All right, so first is left and right. That's inside the parentheses, opposite of what you think. And then it's up and down, it's what you think. All right, so first if we shift everything right 4, then our asymptote would also shift 4. If we shift everything up or down, our horizontal asymptote would go up and down 10. So then our horizontal asymptote would also go up 10. So if you look at the relationship between the vertical asymptote, it's just the opposite of what's in the parentheses. The horizontal asymptote is just what you see on the outside of the parentheses. If it's not there, it's 0. Okay. As the rational function y equals 1 over x is translated, its asymptotes are translated as well. Can you write the equation for the translations described? So the horizontal asymptote y equals 3. Okay, so horizontal would be going up and down. So again, here's your horizontal asymptote. And if it shifts up 3, so does your whole graph. So we know that there's going to be an up 3 shift. And the vertical asymptotes go left and right, and it's at 0. So if we write this just up 3, it's 1 over x plus 3. And that would shift everything up 3. All right, horizontal asymptote at 11. So we know this is up 11. But then everything goes to the left, 9. So how would we write that in an equation? It'd be y equals 1 over, and left 9 is x plus 9, and then up 11 plus 11. Okay, can we go backwards? So here, remember the horizontal asymptote is a y equals, and vertical is an x equals. And they're at 0 unless it shifts. And this graph shifts. There's stuff dealing with a slope too, but that doesn't affect your asymptote shift. So if we have x minus 9, that's to the right 9. And so our vertical asymptote would also shift right 9. Horizontal asymptote doesn't shift. So the domain is everything except 9, and the range is everything except 0. Okay, so these are related right here. So the horizontal asymptote and the vertical asymptote are related to domain and range. All right, let's take a look at this next one. So again, horizontal asymptote is your y equals line. Vertical is x equals. And vertical is left and right. Horizontal is up and down. Okay, so this one goes down 3. So this one goes down 3. This goes left 5, left 5. And the domain, everything but negative 5. Range, everything but negative 3. And you could try graphing too if you want to look at them. All right, so again, we look at our left and right shift up, down. So horizontal is y equals, vertical, x equals. And horizontal is up and down. So here it's up 18. And then here we go, plus 1 is left 1, so minus 1. And then our domain, x can't be negative 1. And our range, y can't be 18. Because there's nothing that exists at the asymptotes. Okay, last question. Can you match the graphs? Okay, so this first one, it shifts everything right 5, including the vertical asymptote. So which is shifted right 5? Let's take a, oh, that would be this one. See how this is shifted right 5? So there's the first one. The next one, it doesn't look like it's shifted. If you look at your asymptotes, they're right there where they need to be. So that's this one. And this one, it goes down 1, and it goes right 3. And if you notice, this goes down 1 for your asymptote. It goes right 3. So this matches up right here. All right, so on your assignment, you're going to see if you can use what you know about past behaviors and apply them to rational functions.